So now we're going to look at both resonance structures and formal charge. I mentioned resonance structures earlier in a video when we were drawing the carbonate ion, and we'll look at that again on this slide. However, resonance is when two or more reasonable structures can be drawn for a compound. And we say the real electronic structure is identical to neither, but intermediate in character. So the real form is a hybrid. They are not different kinds of molecules. They all have the same geometry, but they have different arrangements of electrons in the structure. And when you draw a resonance structure, you cannot change the position of the atoms. Only the electrons in the bonds can be moved. And we have an example here of ozone, O3, and you do see some charges applied to these structures, which will be explained when we move on to formal charge. But as you can see, the double bond in the two structures is in a different location. And that's because each of those oxygens could share a pair of electrons to satisfy the octet rule for that central oxygen atom. Okay? So let's go back and look at carbonate. And I'm just going to draw one of the structures to begin with and not go through the steps. But we have the carbon atom central, and then we have 3 oxygen atoms surrounding that. 2 of them are single bonded to that carbon, but one has a double bond. Okay? And for a proper Lewis structure, we need the brackets and the charge outside. Now, once again, that double bond could have formed with any of those oxygen atoms. So we must draw 3 structures for carbonate, moving the location of that double bond. We do not, again, move the atoms. We're only moving electrons. So there are 3 resonance structures for carbonate. And the last one, we have that double bond on the left side and the single bonds in the other positions. And of course, our brackets. So anytime you have a structure in which there is a double, and this can happen in triple bond structures as well, that double bond could have formed in different location, you must draw those additional structures. Now, an extension of resonance is something we call delocalized bonding. And this is a type of covalent bond in which the electrons are spread over a number of atoms rather than localized between 2 atoms. And these are found, or this delocalized bonding is found in molecules with symmetry and double bonds. And the most common example of this is a molecule called benzene. And this is a cyclic structure. So it's a ring structure. It's made of 6 carbons, and it has 3 double bonds. And we have resonance here. because those double bonds could have formed here, here, and here. But we use these resonance structures to indicate that delocalized bonding. And again, the real structure is an intermediate of these resonance structures. And one way we reflect that delocalized bonding for benzene is just to put a circle inside that six-membered ring, which tells me that those double bonds are in constant motion, flipping throughout that molecule. So now let's take a look at formal charge. And formal charge is the hypothetical charge that you obtained by assuming that the bonding electrons are equally shared between bonded atoms, and the lone pairs belong only to one atom. So what do we use formal charge for? We use it to determine the atomic arrangement when two or more structures are possible. And the example we're going to start with is a compound called formaldehyde, which I'm sure you've heard of. And there are two possible ways to draw skeletal structures for this formula. Okay, and we're going to use formal charge to identify the more plausible of those two structures. So how do we calculate formal charge? The formal charge on an atom in a Lewis structure is equal to the number of valence electrons in the free atom minus the total number of non-bonding electrons on that atom. So these would be lone pairs, minus 1/2 the total number of bonding electrons. Okay. And very important rule, the sum of the formal charges of the atoms in the molecule or ion must equal the charge on the molecule or ion. So formaldehyde is an uncharged molecule, so the formal charges on carbon and oxygen, and we'll talk about why hydrogen doesn't concern us, are going to determine the most plausible structure for that formula. So we're going to look at each of these individually. So we have completed the Lewis structure for formaldehyde. There were 12 electrons. Those have been distributed. And now we're going to calculate formal charge. So the formal charge on carbon and oxygen. We do this individually. Remember, hydrogen is always a terminal atom, only forms one bond, so its formal charge will be 0, and we don't have to worry about that. It's the atoms within that structure that have lone pairs and other bonds associated with them. So the formal charge on carbon, 4, number of valence electrons. Now this carbon atom has 2 non-bonding electrons, so we're going to subtract those. And it has 3 bonds, so 6 electrons in bonding, and we subtract 1/2 times 6. So we get a formal charge on carbon of a -1. Now we do the same thing for the oxygen, 6 valence electrons, minus 2 non-bonding electrons, minus 1/2 times 6 gives us a +1 formal charge on oxygen. Now I want to point something out right here before we move on. that the negative charge, or negative formal charge, ideally is on the most electronegative atom. And oxygen is more electronegative than carbon. So this is an ideal from the start. And of course, we've got a plus charge on the oxygen atom. When we add them together, however, they come up to a net charge of 0. Now let's look at the other structure and determine formal charge for both carbon and hydrogen. And again, the total number of electrons were totaled and the structure, Lewis structure, was drawn, obeying the octet rule, just a different position of the atoms. And so that is our structure, and we need to calculate formal charge for carbon. 4 valence electrons. It has 0 non-bonding electrons, and it has 8 bonding electrons. So 1/2 times 8 is subtracted from 4, and here carbon has a charge of 0, a formal charge of 0. For the oxygen atom, repeat that process. 6 valence electrons minus 4 non-bonding electrons minus 1/2 times 4 bonding electrons. So here we also get a formal charge of 0. Another rule that we want to satisfy is that we have the least amount of formal charge on the elements within the structure. Okay. So, summarizing some of these rules, for neutral molecules, a Lewis structure in which there are no formal charges is preferable to one in which formal charges are present. Lewis structures with large formal charges are less plausible than those with small formal charges. So in other words, we want to minimize the amount of formal charge in our structure. And Lewis structures having similar distributions of formal charges, the most plausible structure is the one in which the negative formal charges are placed on the more electronegative atoms. So between these two structures, which is the more likely structure for formaldehyde? So keeping in mind these are both 0 formal charges. So this is the correct structure for formaldehyde. Now we're going to take a look at a couple other examples before we move on to bond enthalpy. So we're going to look at a molecule that has the formula H2SeO4. Selenium, there's only one. So I'm going to actually draw 2 different structures, one that obeys the octet rule and one that doesn't obey the octet rule. Now keep in mind that selenium is one of those elements that has an empty D subshell. So the one that obeys the octet rule looks like this. We don't have any charge on this structure, or the formula overall, so the formal charges need to add up to 0. Remember, we don't need to be concerned about the hydrogens, but we'll calculate formal charge for both selenium and oxygen. So formal charge for selenium, 6 valence electrons minus 0 non-bonding minus 1/2 times 8 gives us a formal charge of 2+. And we have two types of bonding arrangements for oxygen. So we have to do oxygen twice. One of those oxygens has 2 bonds and 2 lone pairs. And that oxygen, or those oxygens, have 0 formal charge. And the other oxygens have 1 bond and 3 lone pairs. So 6 minus 1/2 times 2 gives us a formal charge of 1-. Okay, so when we total those formal charges, the 2+ and the 2 minus 1s, the overall net charge is 0. So that satisfies the formal charge rules. Also, the positive charge is on the most or the least electronegative atom. So that's good. And the negative charges are on the more electronegative oxygen atoms. But here's another structure for that molecule that does not obey that octet rule. And in fact, it has an expanded octet. And this is what that structure looks like. Now let's calculate the formal charge for selenium and oxygen again. So formal charge for selenium now, 6 valence electrons, 0 non-bonding electrons, minus 1/2 times 12 gives us a 0 formal charge for selenium. And if we go back and look at this bonding pattern for oxygen, we see that that also has a formal charge of 0. So all of these have 0 formal charge. So between the two, when you make a choice, it's going to be some of the rules that I've mentioned when looking at this structure that obeys the octet rule. In addition, with this structure, we want the least amount of formal charge when we make our choice. So this is the most plausible structure for this molecule. Now we're going to look at one more example, and this example involves a polyatomic ion, and its formula is AfO4 3-. And just as a reminder, when we have a charged molecule or an ion, the formal charge must equal the charge on that ion. So for the possible structures we look at for this polyatomic ion, the formal charge must total -3. If we have a positively charged cation, the same rule applies. The formal charge must equal the positive charge on that ion. So I'm going to draw two structures on this slide. and there is a third. I'll have to do it on the last slide because I don't want to scrunch too much into one small space. So the first one I'm drawing follows the octet rule. So it satisfies that rule. And we have arsenic central, of course, and we have the 4 oxygens terminal, making this look symmetrical. And I'm not going through all the steps of drawing the Lewis structure. I'm just going to input all the electrons. All the all the oxygen atoms have the same bonding pattern, so they will all have the same formal charge. Let's start with arsenic. And it has 5 valence electrons, 0 non-bonding electrons, and 4 bonds, so 1/2 times 8 gives us a formal charge of +1. So that's okay. We've got the least electronegative atom has a plus charge on it, and we look at oxygen for this bonding pattern. 6 minus 6 minus 1/2 times 2 gives me a -1. So all of these oxygen atoms have a formal charge of -1. When I total those formal charges, I have 4 negative ones and a +1, so overall charge, and we should also, of course, reflect that this is a polyatomic ion, is 3-. Now the other possible, or one of the other possible structures, there are 2, and neither of them obey the octet rule. Arsenic central, and now we have an expanded octet. This element has an empty D subshell, so it can accommodate an expanded octet. So let's calculate formal charges here. We have 2 different bonding patterns for oxygen. I'm not going to repeat this calculation. We know these are 0 because of the prior calculation. Oh, I'm sorry. I'll do this one. Never mind. It's this one that we did. But for oxygen, with its preferred bonding pattern of double bond and 2 lone pairs, we have 6 minus 4 minus 1/2 times 4 gives me a 0. Arsenic, 6 minus 0 minus 1/2 times 10. Oh wait, 5. This is 5. Sorry about that. So 0 here. And oops, sorry, I made a mistake here. Sorry. We only have 1 double bond here. We'll get to the 2 double bonds. So my bad. I was looking at the charges, they weren't adding up. So this has -3 overall. So just to point out the difference between the first structure and the second, while the first obeys the octet rule, we have more formal charge. Well, actually, we have a formal charge on every atom in this structure. So that's a strike against that. Otherwise, it satisfies the other rules. But if we compare these two structures, we've minimized the formal charge. Arsenic has 0, and we've got an oxygen with 0. So this is looking a lot better than the first one. And let's take a look at the other possibility. And unfortunately, I won't be able to come back to this slide to point out the differences. But keep in mind right now, number 2 is the most plausible structure. And the last possibility is where we have those 2 double bonds. So still an expanded octet. And so for arsenic, we have, now we have 5 minus 0 minus 1/2 times 12. So now we have a 1 minus, or minus 1, on that least electronegative atom, which isn't good. And I'm not going to repeat the oxygens. These are both 0, and these are minus 1. Okay, so the formal charge does total minus 3, but the issue here is that minus on that least electronegative atom. So the second structure is the most plausible structure for this polyatomic ion. Next up, bond enthalpies.